All right, so from my perspective, I'm going to look at one particular service that is related to NDN that is obviously of need when we look at if we can ever realize this in a tactical environment, which is the traffic engineering concept. So basically, we all know, those of us who are involved in anything that has to do with tactical networks, the tactical data links that we have don't have unlimited resources. They have limited resources, and you can't just keep pouring stuff on them. There has to be some sense of what is important and what is not, so that if you can't pass everything through, you have to make a decision. So these are some of the things that I'm going to talk about here. So when we talk about this notion of traffic engineering, what exactly is that? It's the idea of manipulate the traffic so that you reflect what the intent is. What we call sometimes, mission requirements or commander's intent. What is the objective of the network? So this looks at prioritization of traffic, what is important, what is not, shaping traffic, so that we can describe exactly how much of a flow or a set of flows can get through, and also some signaling. If we're going to do define what is important versus what is not, or if there's some sort of a hierarchy, how can we signal that? So there are a bunch of protocols that deal with that. OSPFT is one of them. That they're just catered towards this idea of being able to do traffic engineering in an IP network. So I'm going to look at some of the elements of traffic engineering just at a high level to describe what they are, and then I'm going to go into how can some of these concepts be realized in an NDN environment. So, for example, load balancing. If I have two nodes, source and a destination, I'm trying, and I have two links between them, this notion of load balancing is looking at how do I balance my load, how about balance the traffic that is going across these two links so that I'm not utilizing one of them all the time and not the other. So in this case here, I have two links, 500 kilobit per second and a 10 millisecond, and the second one is 250 and a 1 millisecond, and I'm have two flows, a green and an orange, and I'm kind of balancing the load that I have on both links. There's also this notion of load distribution, which is kind of similar, but in this case, what we would like not to do is to take packets from a given flow and actually split it across multiple links. Right? We want, for a given flow, you take that link, but another flow could take another link. And so in this case, I'm distributing the load over multiple links. And we'll talk about that a little bit. This is actually more of a desired functionality than the previous one, because the previous one causes some issues. Then there's also the notion of different objective functions. The notion of what is important from a flow A perspective versus a flow B perspective could be very different, right? So there's one flow that requires latency, another one that requires data rate. So the objective function here is what are you trying to accomplish? What are the quality of service requirements? So the green flow here, there's a lot of it needs data rate, so it goes over the 500 kilobit per second. The orange one, not much, but it really wants delay. As low delay as possible. That's the primary objective. So I send it over the lower data link, but it also has lower delay. So that is the outcome of an objective function. Then you also have different types of traffic. You have broadcast, you have multicast, you have unicast, and all of them correspond to flows. And you have to cater to their individual requirements. So the source here is sending three different types of flows. The orange one is unicast. It's going to D1. The blue is multicast. It's going to both D1 and D3. The green is a broadcast. It's going to every node. And so each one of them, you have to account for how much of the links that you have they're going to utilize. Some estimation and measurement. So you need to have an understanding of how much the resources that you have, the links that you have, what are their reliability, what's their latency, what's their data rate. You need to have an idea about the demand on the traffic, right? How much, for this flow versus that flow, how much really is being sent. And so you can do that by measurements, or you can do that by having a reservation-based model. And then this notion of a priority signaling, how to identify, what is important, highest versus middle versus lowest. And traditionally, we've been using the DSCP differentiated service code point component with an IP to signal that, right? So we have 64 different priorities that we could utilize, and we mark packets to reflect that. Okay, so all that is good. One aspect of it is when we do these kind of signaling for traffic prioritization, who's responsible for doing it? There are two models here that you can look at. An application could signal. It could say, I am the most important thing. So this is, I'm going to mark my packets as this most important thing. But then you get this tragedy of the commons where everybody thinks that they are the most important thing. But then you also have some sort of inline devices that could do prioritization where you have a policy that you could use, and you can have that policy be a network policy as a whole. So it's more of an administrator puts in place as opposed to applications claiming it. So how do we do this today? This is how we do this today. This notion of traffic engineering, it is, the QoS signaling does happen. It does happen for the most part through these inline devices. We place them in the network. We put policies on them. These policies would say this is important, this is the second important, this is the least important. And as packets come in, we apply these signals on them. But all these are anchored off of TCP/IP header information. So you basically look at the 5 tuple. You look at source address, source port, destination address, destination port, and protocol. And based on that, you make a decision. Is that the right granularity, right? Do we want to go deeper? I mean, to me, when you're really talking about quality of service, you're talking about the content. But we're really anchoring it here off of end-host information, right? I could do better if I actually have an idea about what's in this packet, what's the content for real. So we do per flow granularity, looking at these 5 tuple, and we do these concepts. So in this case, these packets come in marked. I have my traffic engineering algorithms that I use. They look at all these packets and they compute path, and they come up with that decision where the green flow goes on the top link and the orange flow goes on the bottom link. But it's all anchored off of TCP/IP information. Why is this approach limiting? This approach is limiting because we're not reflecting the content, as I said. We're reflecting end host or endpoint semantics. I can have different chunks of data that actually have different levels of information at different with different quality of service requirements, but I'm losing that just because they're all part of the same flow. And so given the dynamics and the challenges of tactical environments, what you really want is something that is more adaptive, something that goes more granular. And I'm giving an example here of cursor and target, which is one where we signal information like positions, position information and things like that. And you use that to identify different targets, right? There's a hostile target, there's a friendly target. Right now, because all this information, if you look at the TCP/IP header information, it's all going to look the same. So I'm going to treat it all the same, right? But maybe the hostile target needs to be treated differently from a friendly target. I mean, if it's a hostile target, I probably want to disseminate this as fast as possible. Right? So maybe the delay requirements here will be different, but I'm losing that because I don't have that granularity. I can't go deeper into what's in the data packet. So let's look at some of these concepts, and if we're going to realize some of the NDN functionalities, to be able to have a better traffic engineering or better sense of traffic engineering, what tools do we have? What capabilities that we have that is offered by NDN that would allow us to do that? So I laid it out as, more or less 4 different dimensions here. So I'm going to look at, where's the signaling coming from? So in NDN, we have the notion of a producer and a consumer, right? The producer produces data, the consumer asks for it. So who really can ask for the quality of service here, right? I can produce data, and that data could be consumed by different people. But, the importance of this data to consumer A versus consumer B may be different. Maybe some wants it right now, maybe some not necessarily. So I can make a call as how the information is important in general, but I also need the granularity where every consumer could ask for it at a different level of quality of service. So we're going to look at, producer and consumer-driven quality of service. This notion of caching also has an important place here because when you cache data, you can get it actually faster. right? So because you don't have to go all the way to the end host that produces it or to the producer and grab it. If it's in the network, I can probably get it faster, and I can also, have more resilience. Be able to access it when I can't get to the producer. So we can look at how can we have QoS aware caching policies, right? How can I, when I'm making caching decisions, I'm caching this piece versus that piece, right? I don't have unlimited caching. I have limited space. At some point, I may run out of space. So then the decision has to be, what should I purge? What should I keep? And if you have some sense of quality of service awareness here, you can base your decisions based on that. Then there's also this notion of a forwarding strategy. When you're forwarding packets, NDN packets, whether it's interests or data, you have to make a decision. How are you going to forward it? You're going to send it across this link, across that link, across both. You're going to send it as broadcast. You're going to what exactly are you going to, how exactly are you going to forward it? And you can also base that, based on awareness of quality of service requirement. And so if we're going to realize this quality of service as a policy, right? It's a policy that is network-wide, right? Everybody has to synchronize on that policy, right? Because I don't want to make a decision that is different from someone else. We have to have like a network-wide, system-wide policy that everybody agrees on. So how do I do that agreement? So we're going to leverage some of the concepts that Alicia has talked about, synchronization, using some of these sync protocols so that I can define a global policy, right? And then be able to update it and change it and things like that, but at the same time synchronize it. And then when we come to updates and changes, we have to have some sort of a hierarchy. You can't just have everybody update, right? You can have different pieces within the policy are owned by certain people, right? So maybe a shore site, they are the ones who are responsible for updating this component of the policy. But elsewhere, anybody could update. So you can have some sort of access control on top of it. So this notion of QoS signaling, when it's producer-driven, right? So when I'm producing data, right, I give it a name, right? And that name, I could actually put in the name some of these quality of service requirements, right? So that when someone is looking at that, when a forwarder is looking at the name of the packet, they can actually infer from it what's the type of treatment that you want to provide for it, right? So I could put something like this, where I say, okay, so the name of the packet is really only the first 5 components of the name, but the last piece you use to infer what level of quality of service you're providing to it. So here it says, latency max 2 seconds. So then or 2 milliseconds, right? So in this case, the forwarder would look at, given that requirement, how do I forward this? Can I do that? I'm going to try to honor it as much as I can. And so in this case, if I have COT data that is friendly versus hostile, I can tag to each a different number. And so then I could disseminate each one of them using a different using different QoS. So this is basically explicit. I tag on the packet exactly what I want to have in it. There could also be implicit. So in this case, we'll have a policy. And this policy basically says anything that says mission ACOT ground hostile, by default, when you see that as a prefix in the name, you should assume this requires reliability and low latency. I'm not going to tell you exactly an exact number, but I'm going to tell you when you forward this, make sure you pick the lowest latency path, right? But then when you see something like mission ACOT ground friendly, reliability, it doesn't necessarily have to take the lowest latency path, but just make sure that it's something reliable. So in this case, each data in itself, each chunk of data will have, or each name prefix really, will have its own different QoS signal, and it'll be based on the policy of the network. And so basically, when this comes in, the forwarding strategy would look at this, and then it'll make a decision as to how do I forward this? What would be the best way to do that? So how about the consumer? So this was the producer side. The producer is really generating the data and it's tagging this on it. How about the consumer, when the consumer is asking for the data? So how do a consumer ask for data? They send an interest packet. And what's in the interest packet? In the interest packet, there's a name of the data that they want. The interest packet also has an interesting piece at the very end of it, which is called application parameters. There, you can actually specify customized parameters per application. It's more or less, just an open, an extensible piece where you can add application-specific things. And so in there, you could provide that information. You could say, okay, I need the packet with that name, and here are my parameters. I want it fast. I want it as fast as possible. So then the consumer is driving the quality of service requirements in this case. So this would be another, the sort of the consumer's perspective of how do they can provide this QoS signaling. So then the forwarding strategies then would have to try to honor some of these requirements. So how do they do that? So they have to have awareness of what is available. What are the communication resources that they have? How reliable they have are these communication resources? And what's the latency on them? So if I have a path, between the source and the destination, I have two different paths, right? Like the figures that we had before, right? And I think it's one of them is 500 kilobit per second. Both of them are 500 kilobit per second. I don't know exactly what the delay is on each. How do I know that? So it is, using this interest data exchange, where I can forward an interest over a link, and because NDN is stateful, it keeps this information in the pending interest table. I forward this interest over the interface, and I put the time when I did it. When the data comes back, now I know what the round trip time is, right? And so using that information, I can have some sense of latency. What is the latency over this link versus that other link? I could also have information about loss, because if I forward it and I never hear anything, potentially there's loss on that path. So I can factor that in, right? So this feedback loop where interest and packet come in, in and out, could give me some information about the reliability and the latency, and I can factor this into that decision making when I'm trying to pick the right path for a given data packet. And I could do that per class of service, so I could do that per namespace if I want to. Right. So this is basically this idea. Leveraging this in-band interest data feedback loop to be able to measure. So I know when I sent things, and I know when I received the data back, and I can look at the time and be able to figure out how long. So you can base it on the quality of service signaling really could come from the consumer or the producer, and then use the feedback loop to be able to measure what you have. Then looking at the load balancing and load distribution. So I talked about this, defined what load balancing is, I defined what load distribution is. So this notion of load balancing, where I take data and I really balance it across the links that I have, we really try to shy away from that as much as possible, just because specifically for TCP flows, if you take data and you send it across two links, you get different senses of latency, and it screws up your congestion control completely, right? It just becomes, congestion control will not function the way you expect it to. So traditionally, we try to avoid doing that. We try to do more of the load distribution, where every flow follows a given path, but we take packets from a given flow and spread it. But if we look at from NDN's perspective, even if I use NDN over IP, I can leverage TCP and UDP. It's not an end-to-end. I think it's only just used between NDN nodes, right? So in this case, it's a little bit different. It's not end-to-end connection. It's only just on a per hop basis. So I can have a forwarding strategy that actually goes and says, when I see packets that have this name, always send it across this link because it's reliable and it wants to do that. When I have another one that has this name, send it across this other link. When I have a third one, I don't necessarily, have a preference, this link or that link, so I can actually send some across one and some across the other, and that's okay because it's not an end-to-end path; it's just a per hop. So this is sort of another example here where I can also use this forwarding strategy to decide whether I unicast, multicast, or broadcast, right? So let's say the example here, mission ACOT ground hostile. This is important information. I need to disseminate it as fast as possible. So what do? I blast it out. I broadcast it across all links, right? Granted, there are issues with that. You're using more bandwidth, but let's say this really needs to get there as fast as possible. Right? So then I forwarding strategy, which is to send this across all the links. I want this to be delivered to everybody who wants it. And even if someone doesn't want it, you could enable something which we call opportunistic caching, right? An NDN node if it receives a packet that knows nobody asks for, but it thinks that someone might, right? It could still cache it, right? So that when a request comes in, you deliver it. So that is possible. But then you get something else that says, COT ground friendly latency X. So in this case, send it on any, whatever interface you have where the latency on that interface is less than half of X. So that just, X is really the round trip that you want. And if this is just a latency one way, so the round trip would be 2 times that. So you just send it over any link that has half of what is requested. Another one which says, file, I'm going to do a file transfer. Okay, so this is where capacity is needed to send it across the link that has the highest capacity. And then the final piece of this is the caching strategy. How do you, what do you cache? What do you remove from the cache? How do you, what strategy do you use to put things in the cache and remove things from the cache? So what we call insertion and eviction policies. They can all factor quality of service requirements, right? So if I know that that is something that is latency sensitive, I want to keep it in the network so that when people ask for it, they get it from a closer place as opposed to from the actual producer or the end host. So if I keep it in the network, then I could get it much faster, right? You could also factor in the value of information over time, right? So maybe this information that I'm talking about here is position location information. So what I want is the latest. I don't want older ones. So maybe anything that is older than a minute, I don't care about. So when you're trying to delete, you don't just delete randomly. You delete the ones that are older than a minute. So you factor that into your eviction policy. You can also factor the reliability of the link. So if I know that the data that has this name, it's always, or the producer for it is always, I can only reach it across this link. And this link is really very unreliable. It's up and down, it fluctuates, right? I don't want to, if I remove it from the cache and the request comes in, now I have to somehow traverse this link and go ask for it again. So keep it then in this case. Factor in the reliability of the link as an example of that. And these are just examples of that. So retain only latest sequence of a chunk where the older sequence numbers do not matter, right? If position location information, only the latest matter. The older ones, I can just remove them. Retain chunks longest when the only path to retrieve them is through an unreliable link. So keep that as long as you can.
I have a question. You mentioned that you choose the link, and for example, for reliability purposes. So the underlying link selection and sending on the link is based on the core TCP IP idea, or how does it work?
So basically, so NDN nodes have what we call faces, or equivalent of a connection between them, right? And this could be anchored off of a TCP or a UDP connection. So you can have a UDP face between 2 NDN nodes, or you can have a TCP face between NDN nodes. But this is not end-to-end, it's just on a link basis. So when I say a link, it's really that, like TCP or a UDP connection, or I could also go straight over Ethernet between 2 nodes.
And so the same, for example, if you use some variations of Bluetooth.
Right, so in this case, I'm just going over Bluetooth directly, I'm bypassing a transport. So a link is really just what connects to NDN nodes. What is it? NDN doesn't tell you what it is. You could do a TCP, you could do an IP, you could do a broadcast, you could do a straight over layer 2, whatever you want. Okay, and then the final piece of this is the policy synchronization. So if I want a global policy that speaks to what is important and the relative priority, the relative importance of things, I want to synchronize that. And I want to be able to synchronize it in a manner where we all agree on, right? But we can change it, in a way that is controlled, right? So traditionally when we say, quality of service policy, I could have centralized policy where everybody has to agree on. Nobody could change this except for an admin. Let's say that admin sits somewhere. He's the only one who's allowed to change that. But I can also have my local policies, things that are really important to me. And I need to distinguish between these two, right? So if there's something that is global, everybody has to agree on, then okay, so you're not allowed to change that. And so in this case, we could look at these as data in the network that is signed by an admin, and that admin sits in a command center. Right? If any update to that data has to have the signature of that admin, right? And if I get data that doesn't have the signature of that admin, I'm not going to update my policy. This is where you do some level of access control, right? But then there's another set that is mine, so I can control that. So I can devise my policy locally. And then you can define the relationship between these two, right? If I have my local policy and then a centralized policy, and I look at, oh, they are in conflict. So the centralized policy takes precedence. So all that is enabled by being able to use things like sync protocols to synchronize the policies, but at the same time look at who signed this. Is it an admin or is it local? And if they are in conflict, then the admin policy overrides. So things like that would be enabled by using something like a sync protocol and access control mechanisms, which is what Alex and Nisha talked about.